Today I want to show you how to get started using TemplaBuild to make your container builds faster and more reproducible. We'll start with the basics on how to use source and base image locking, and then move on to look at its multi-platform support and how its templating engine can be used to support multiple build profiles for your project. To start, let's look at a Docker file for a simple application we're working on. In this example, we're building on top of the Python 3.10 image, installing a few OS packages as well as a few Python packages. Using existing build tools like Docker, we might build our image with a command like this. The first thing that's going to happen when we start this build is the builder will download the latest Python 3.10 source image, or it'll use a locally cached version if available. In this case, this is an image maintained by the Docker community and may update from time to time with various bug fixes or security updates. This presents a problem when trying to make builds reproducible, however. Two people who attempt to build your image may be starting with different versions of the original source image. Just as we use package locks for our application dependencies, TemplaBuild helps address this by creating a lock file for our source images. To take advantage of TemplaBuild's source image locking, we only need to give our build stage a name, which will be used as the default tag for our image. Then we can use the TemplaBuild command line interface to create our image. TemplaBuild works by pre-processing our Docker file and passing a rendered build context to the underlying builder, in this case Docker. Now when we build with TemplaBuild, a lock file will be created that will map each reference source image to a fixed digest. We can inspect the file .templabuilddata.json to see this lock metadata. We can verify that the digest present in the lock file matches the digest used in the build. Now let's move on to the remainder of our build. In the case of our OS package installations, we haven't locked to a specific version of any packages, so they may change from time to time. For our Python dependencies, we may or may not be using a package lock file. In either case, these installations can be time-consuming and may break reproducibility. TemplaBuild helps here by allowing us to organize our build into base and top-level images. The idea behind base images is that they should contain parts of the build that change infrequently but are time-consuming to run. TemplaBuild will allow these portions of the build to be built once and shared between all developers through a registry. The remainder of the top-level image should just be installing application-specific code and configuration. To take advantage of this, we need to break our Docker file up into two stages, a base stage and a top-level stage. By default, TemplaBuild will treat any stage name that starts with base as a base stage. Then we'll start a new top-level stage that picks up right where the base stage leaves off and installs our application. Before we can use this feature of TemplaBuild, we need to configure where we're going to store our base images. For this demo, I'll use a registry I'm running locally. Typically, you would want to use a registry that's shared between your developers. We configure this by editing the file templabuild.yaml. If you want to experiment with TemplaBuild and don't want to use a real registry, you can run one locally using a command like this. With that set up, now we can run TemplaBuild base build to build all of our base images. Inspecting the build.data.json file again, we can now see the image digest of our base image as well as its content address. TemplaBuild can automatically detect and rebuild any base images if any of its inputs ever change. This is especially useful in continuous integration environments as it allows you to verify that the build instructions match what is currently cached in the build.data.json file. Now when we run TemplaBuild build, we will just build the application portion of our image, starting from the base image we already built with the base build operation. Like we did with source images, we can verify that the image digest of our base image matches the image digest used at the start of our build. By default, TemplaBuild will build for your current platform. For me, that's Linux AMD 64. Suppose, however, we wanted to support multiple platforms. TemplaBuild can support this directly by listing the platforms we want to support in our TemplaBuild YAML file. Let's try doing this for AMD 64 and ARM 64. After adding a new platform, we need to rerun the base build command. This will by default build for all platforms, but we can split up the build by platform if needed. In my case, my builder is set up to build for either architecture, so this is not a problem. We can now see that the build data.json file has entries for both of our configured platforms. Now we can run the build subcommand to build our top-level image. By default, this will build just for my local platform. We can see that the base image digest used matches the digest for AMD64. We can build for a different platform by passing the platform flag. Again, we can verify that the appropriate base image was used. Template Build can also support creating multi-platform images using the publish subcommand. To take advantage of this, we first need to configure where we want to push our images. In our case, we'll just use the test registry again. Now when we run the publish subcommand, we'll build for each platform and then push a single multi-platform image to our registry. The last feature we'll talk about is using profiles, which allow us to templatize our builds and share common build logic. When using Template Build, our Docker files are actually Jinja templates that render to Docker files. At this point, our Docker files contain no templates and can still be built using a conventional image builder like Docker Build. Using profiles will break this compatibility, but give us a lot of power to share build logic and support multiple image configurations. Let's suppose we want to build a dev and a release version of our application. To do that, we edit our Template Build YAML file and define our two profiles. Within each profile, we can specify arbitrary YAML data that will be passed to the template as a parameter. Here we'll specify an install dev packages key that we can use to templatize our build. We'll specify that we want dev to be our default profile. Now in our Docker file, we can reference these profile variables to templatize our build. In our case, maybe we want to install an editor into our dev image that we don't want to be in our release image. We can also have our templates reference other information like the name of the current profile. Here we'll pass the reload flag to Uvicorn if we are using the dev profile. Since we've made changes to our base images, we'll want to rerun the base build subcommand. There are now 4 different base images we're going to create, one for each combination of platform and profile. Template Build is smart enough to combine work that is shared between each of these builds. In this case, however, it recognizes that it has already built an image that's identical to the release image and is only building the dev images. Now we can use the build or publish subcommand to build our images. This will build against the configured default profile, in our case dev, unless we pass an alternate profile name with the profile flag. That's it for this video. You can get started with Template Build yourself just by downloading Template Build through pip. Links to the open source repo and documentation can be found in the comments. Thanks for watching.